By now, the assumption is you have watched the 2-hour documentary on dark matter and dark energy. If you haven't watched it yet, I would suggest you do that first before watching this video. It's not essential, but I think it will go a lot better for you to do it in that sequence. That said, assuming that you have watched the documentary, there's a lot to unpack, as I'm sure you have seen already. So we're going to recap some key points from that documentary. We're going to discuss a few things, and hopefully what we'll also see is that it begs that we get into some serious background in order to get up to that finish line of dark matter and dark energy. So page 1 in your lab manual, that's where we're going to start. Topic 1, dark matter, dark energy. We'll start with percentages. The percentages of dark matter, dark energy, and normal matter in this universe. For dark matter, roughly 23%. Dark energy, roughly 73%. Normal matter, that's us, roughly 4%. Now, some of you have already noticed by doing some additional research that those numbers tend to vary a little bit depending on who you're reading. And that's kind of the nature of the business in this sense. This is still new territory. It's a moving target, and so we're going to see some variation in these numbers. Not much, but they're going to slip and slide a little bit left or right. So some assessments will have normal matter at 5%, some will have it slightly less than 4%, but generally speaking, that's what we're looking at. And now what we're doing is we're fussing over decimal numbers, decimal points. And again, that's fairly typical for something as new as this. Several key figures to be aware of in how we got to this understanding of dark matter and dark energy. Number 1, Vera Rubin. Number 2, Fritz Zwicky. And number 3, Big Al. Those are the big 3 that we're going to look at. Obviously, there would be a whole panoply of other players to look at, but we're going to focus on these 3. So we'll start with Fritz Zwicky. I need a little more room here. So Fritz Zwicky, in the early 1930s, he studied and observed orbital speeds versus visible mass of galaxies in the Coma cluster. And the Coma cluster is observed in the constellation or asterism Coma Berenices. All right, what is the Coma cluster? Well, the Coma cluster is, number 1, approximately 300 million, or 10 to the 6th, light years distant. Number two, it contains more than 1,000 galaxies, not stars, galaxies. Just think about that. Over 1,000 galaxies. Galaxies which contain billions of stars. These galaxies are gravitationally bound. Which means that they're orbiting one another. So let's just pause here. What we're talking about is over 1,000 galaxies that are orbiting one another like a swarm of bees. They're gravitationally bound. And remember, what do you got to have in order to have gravity? You got to have mass. Mass means gravity. And these over 1,000 galaxies, by virtue of their mass, are orbiting one another, just like planets orbit the sun. All right. So he observes this cluster of galaxies and he calculates their speeds. He calculates their speeds using red or blue shift. He calculates their mass by measuring their luminosity, their brightness. All right, so let's pause here and kind of unpack some of this. And this gets us to what we need to discuss in terms of fundamentals. He calculates their speeds using red or blue shift. Well, what is that? Well, that is a manifestation of the Doppler effect. The Doppler effect has to do with how waves work, whether it's sound waves or light waves. It has to do with the behavior of waves and the velocity of wave sources. So that's a piece of astrophysics, or physics itself, that we're going to have to get into. We need to understand how this works. How do astronomers measure speeds? This is how. So we need to understand how waves work. Earlier on we were talking about these galaxies being gravitationally bound. That means that we're going to have to get into how gravity works. That means that we're going to have to go all the way back to Sir Isaac Newton. And so, yeah, we need to understand how gravity works. Mass versus luminosity. Astronomers use a kind of a rule of thumb calculus to determine the mass of a luminous object by measuring its luminosity. There is a rough rule of thumb rule that works out pretty good in determining the amount of mass that is represented by an amount of brightness in a light-emitting object. And so the point is, Fritz Zwicky was able to fairly accurately measure the speeds at which these galaxies were orbiting one another, and he was also able to measure fairly accurately the mass that each one of these galaxies represented. what he discovered was this. He determines that the speeds were too fast. The speeds were too fast for the observed quantity of matter. Oh, I should spell that better, shouldn't I? The speeds were too fast for the observed quantity of matter. Quantity of matter, that's mass. We have to understand what we mean when we say mass in the physics, in the sense of physics. Sir Isaac Newton defined mass two ways. He said, number one, mass is a quantity of matter. He also said that mass was a measure of inertia. Well, what's inertia? Well, inertia is resistance to a change in motion. Okay? So the more mass you have, the more resistant you are to a change in motion. We'll get more into that later on. But again, this tells us that we need to get a good, clear understanding of what Sir Isaac Newton had to say about a few things several hundred years ago. So he discovers that these speeds were too fast for the observed quantity of matter. Let me see if I can clarify that. If the sun, we know that the Earth orbits the sun. Earth orbits the sun because the sun has gravity. Gravity is going to pull the Earth toward the sun, but the Earth has a certain speed that keeps it from crashing into the sun, so it stays right in a nice orbital balance. If the sun had more mass, it would have more gravity, and it would tend to pull the Earth more toward the sun, obviously. So how would the Earth not get pulled into the sun? Well, it would have to move faster to counteract that increased pull of gravity. Okay? So likewise, this is what Zwicky is discovering. For these galaxies to be spinning around as fast as they are, it would require there to be a whole lot more mass exerting gravitational pull. But he's not observing that mass. So something's up. And so these speeds were too fast for the observed quantity of matter, and this goes directly to Newton's laws. And he calculated that there had to be roughly 400 times the observed mass for this to occur. Unfortunately, poor old Fritz Zwicky was largely ignored. All right, so I'm going to pause here and flesh this one out a little bit more too. One of the other things that we mentioned here at the beginning of this is we mentioned the distance, 300 million light years. These galaxies are distant from Earth by a range of 300 million light years. How do you measure that? How do astronomers do that? Well, they use something called a standard candle. You don't need to write this down. This is just part of our conversation. What is a standard candle? Well, we're going to get into that in some depth. A standard candle is an object, typically a type of star, that has a certain brightness, and by that brightness we can measure its distance. It's something called the distance luminosity modulus. In other words, we're going to have to get into how we measure distances based on brightness. And if we're going to use these things called standard candles, which are stars, then we need to understand how stars work. So we're going to spend some time looking at how a star does what it does. And believe it or not, if you're going to understand what a star does and how it does what it do, you need to understand how atoms work and how they do what they do. So we're going to have to get into some depth about that too. Now, I say that Fritz Zwicky was largely ignored. Science doesn't occur in a vacuum. It's something that is done in the course of human events. In fact, if we want to define, science itself, what is science? Well, it's the understanding of the natural world. But the question is, who does the understandings? And the answer is us human beings. All right, so it's a very human thing. Science is human because it's humans who do the understanding. It's not just a litany of facts. The facts of science exist whether we are aware of them or not. The facts of science exist whether we exist or not. But the understanding is done by sentient beings. So I say that despite the unfair description of science as being cold and inhuman, I say science is as human as it gets. And so we can't ignore the human element when we try to look at how we got to where we are now. And that gets us to this fellow right here, Fritz Zwicky, and I say that he was largely ignored. Why? Well, there's really no nice way to say it, so I'm not going to try. Fritz Zwicky was an arrogant ass. He was brilliant. He was a brilliant astronomer, and he contributed a lot to the field. But he was so obnoxious, nobody wanted to give him the time of day. Here's a true story of just how much of a dingbat Fritz Zwicky really was. Have you ever noticed that stars twinkle? Why do stars twinkle? Well, it's because of air currents that will bend the light as it comes in from space. And so that's what you're seeing, is you're just seeing air currents when you see stars twinkle. Well, Fritz Zwicky was working at an observatory one evening. He had a young intern working with him, and he saw that the stars were twinkling quite a bit. There was a lot of air currents that particular night. So, true story. This is not apocryphal. This is a true story. Fritz Zwicky hands this young kid a rifle and tells him where to point the rifle, where he wants to direct the telescope, and shoot a bullet into the air to smooth out the air. And the young intern, he's just, well, okay. So out he goes, shoots a bullet into the sky to smooth out the air, and of course it doesn't work. But that's just, that's typical of Fritz Zwicky. He was, more often than not, he was the smartest guy in the room, which is fine. Somebody has to be. But he wasn't content just to be the smartest guy in the room. He wanted you to know that he was the smartest guy in the room, and he would tell you so. So it's no surprise that he was largely ignored. But he was right. He was absolutely right. Now, how was he able to figure out that there was that the mass calculation wasn't working? Well, here's one way to illustrate that. And again, you don't need to write this down because we're going to be getting into this in some depth a little bit later, but I'll just show it to you now. This is part of our conversation. That is Sir Isaac Newton's version of Kepler's third law of orbits. We haven't done this yet. I don't expect you to be familiar with this yet, but we're just going to use it today to illustrate the point. What it talks about, what this formula talks about, is the period of an orbiting object, whether it's the moon orbiting the Earth orbiting the sun, Galilean moons orbiting Jupiter, it doesn't matter. This is how orbits work. And it talks about the period, the time it takes an object to go around once. That's the period. It talks about pi, which is about roundy things, and orbits are roundy things. A refers to the distance that an object is from its primary. So when I say primary, the Earth is the moon's primary, the sun is the Earth's primary, and so on. So it's talking about the distance at which the object is orbiting. G refers to something called the universal gravitational constant, which we haven't talked about yet, but we must if we're going to be doing astronomy and cosmology. And M refers to the mass of the primary. Now, you can do a little bit of an algebraic razzle-dazzle with this formula and rewrite it so it goes like this. Okay. Now, here's what it's saying. If I know the distance at which an object is orbiting, if I know the period, the time it takes that object to complete one orbit, and I know what the gravitational constant is, the gravitational constant is just a number for our purposes. We need to know what that means, but that comes later. But if I know all of these things, then I can figure out this. And this is what Zwicky did. Now, if you look at this formula here, this is pretty cut and dried. A 4 is a 4 is a 4. It's not going to change. Pi is pi. It ain't going to change. The distance, yeah, we can measure that. Pretty simple stuff. It's just simple. It's a simple measuring proposition. G comes right to Newton's law of gravity. Gravity works, boys and girls. So that number has been tested and tested and tested and tested and tested. All right, we know that number works. And the period, sure. Yeah, we know how to tell time. We can tell how long it takes an object to go around one time. This is what Zwicky did. He was able to measure all these things very, very precisely, which would give him the mass of the primary, the mass of the object being orbited around. And that number came out to be roughly 400 times what he could directly observe. Remember, astronomers can fairly accurately use a luminosity scale to measure the amount of observable mass in an object, like a galaxy. And the number kept on coming out 400 times bigger than it ought to be. Oops, something's wrong here. This, by the way, is how we were able to discover the supermassive black hole in the center of our own galaxy, but that's for another exercise. All right. So, again, don't bother writing this stuff down. This is kind of a preview of where we got to go and how this stuff works. All right, so now we'll go to page 2. Vera Rubin. Okay. So now we get up to the 1960s. Vera Rubin, quite a remarkable lady. So in the 1960s, she saw research opportunities in an area Okay. So she sought research opportunities in an area not already overpopulated by male colleagues. Well, what are we talking about here? Well, it is the 1960s after all. And make no mistake about it, it was a man's world back then. It really was. And so she's, I don't think she's at a postdoctorate level at this point, but she's certainly, she's doing postgraduate work. So she's trying to do postgraduate work in astronomy. And yeah, it's very much a male-dominated field. And if she got into research that every Tom, Dick, and Harry was already doing, you know, she'd certainly get lost in the sauce. She's not going to make a name for herself. She's just going to, you know, she's just going to be one of the many minions. So she wants to go for something a little bit different. What she chooses to do is she began to do follow-up on Zwicky's work. Okay, I'm going to underline this, rotational velocities. Okay, recall, Zwicky's looking at orbital velocities of clusters of galaxies. What Vera Rubin does is she looks at the rotational velocities of individual galaxies. Okay, remember, a galaxy is a cluster of stars. Those stars are all gravitationally bound, orbiting this central point in a spiral galaxy. And she observed that further objects on the outer edges of these galaxies, stars, did not decrease. Okay, they did not decrease orbital velocities as predicted by Kepler, who preceded Newton. All right, both Kepler's laws, Newton's laws, for whatever reason, they didn't seem to be abiding by these well-established laws of physics. And again, just to put it in plain terms, the closer a planet is to its primary, the faster it's going to zip around, which would make sense. It's closer to the primary. It's getting more. It's getting more gravity, so it's got to go faster, so it doesn't crash into the sun. Okay, so that's why Mercury goes around the sun faster than the Earth, and Mars goes around the sun slower than the Earth. Jupiter goes even slower. Saturn goes even slower. So the further away an object is from its primary, the slower it's going to go. That's basic stuff, and it's been observed, documented, measured. It works. But why isn't it working on a grand scale, on a large scale, in a galaxy? And clearly, it did not. So, again, something is very much amiss here. And overall, what Vera Rubin was able to measure is that these outer objects were moving approximately 10 times too fast. So something is missing here. Either the laws of physics are wrong, or this mass that we can't detect. So she presented her findings in the early 70s and was largely ignored and dismissed. Again. But her findings were ultimately verified and accepted in the 1990s. So a little bit more about Vera Rubin. It may seem like I'm overemphasizing this piece of it, but it's almost impossible to overemphasize it. It was a very sexist environment that Vera Rubin was working in at that time. And if I may be so bold, it probably didn't help that she was a rather attractive woman. So she's trying to present these findings in a symposium in the 70s, and like we hear so much now, not only is she at this point, trying to maintain a professional career, she's also trying to be a mom and taking care of babysitting and all that stuff, and so she gets all that put into place, shows up at the symposium, presents her finding, and pretty much the reaction was, believe it or don't, oh, ain't she cute? And that was how she was treated. She went into a great depression afterwards and said, oh, to hell with all of you. I'm going to go home and raise my kids, and you can all just go, and that's pretty much what happened for several years. And then she did eventually get back into the field. But yeah, it was devastating for her. And this gets to another soapbox that I get on from time to time, the Nobel Prize Committee. To date, there have been, I think, two women who have received Nobel Prizes in the sciences or mathematics. And if ever there was a candidate for a Nobel Prize, it was Vera Rubin. The sticking point with the Nobel Prize is you have to be alive. And Vera Rubin passed away only a few years ago, but prior to that time, there was mounting pressure on the Nobel Prize Committee to put her in for a Nobel Prize in physics, and it never did happen. And it's the view of quite a number of folks that the Nobel Committee really got a black eye for that one. She was long overdue for a Nobel Prize, and they're not done posthumously, so there you are. So And there's some more stuff that you can read on Vera Rubin in the on the website. I've included some stuff there. If you're interested, I encourage you to read that. So now let's get to Big Al. Okay, still on page 2. So, Albert Einstein, how does he figure in this? Well, this goes to another line of evidence for the existence of dark matter, something called gravitational lensing, predicted by general relativity, and that would certainly be Albert Einstein. Okay, gravitational lensing is a phenomenon predicted by Albert Einstein in his theory of general relativity, published in 1915. It works this way. Number one, gravity is the bending of space-time caused by mass. Two, curved space curves or bends the path of light. Three, a massive object can cause multiple images of distant objects. Okay, a massive object can cause multiple images of a distant object. Okay, this lensing was finally observed with the Hubble telescope in the 1990s. And what we observed were, one, multiple images, and intensified images. Okay, a lot to unpack here. Now you see at the bottom of your page there's a little chart that I put there that kind of outlines what we're talking about in terms of how light can be curved given a large quantity of mass or material. Okay, so general relativity. That redefines how we look at gravity in this universe. Space-time. Space-time. Again, that means that we're going to have a discussion about relativity. So guess what, boys and girls? We're going to spend some time talking about general relativity. And in order to understand general relativity, first we got to talk about special relativity. This is how we're going to understand how space and time work in this universe. And if we're going to talk about how the universe works, yeah, we have to understand how space and time are actually two sides of the same coin. We need to know that. This idea of curved space, that is all about what general relativity is. We need to understand the nature of space. We need to understand how curved space curves the pathway of light. And so how does that relate to our discussion of dark matter? Well, if we can accept that mass causes gravity, or rather gravity is the curvature of space-time caused by mass, and if we can accept that this curvature will bend the pathway of light, then there should be a direct relationship between the amount of mass and the amount of curvature, and there is. And so this is how astronomers now can get a measure of how much missing mass there is in, say, a cluster of galaxies. And again, have a separate line of evidence for the existence of dark matter. So now we've talked about two different lines of evidence for the existence of dark matter. One of them has to do with orbital velocities of galaxies in a cluster and orbital velocities of stars within a single galaxy. So there's one line of evidence. The second line of evidence is curvature of space-time that we can measure, we can detect and measure and index it directly to the amount of mass that has to be in play. Third line of evidence we're going to talk about on the next page, page 3. Temperatures in the intra-cluster medium. Well, that's a fancy way of saying the space in between a cluster of galaxies. All right, so these temperatures we've been able to measure are in the range of tens of millions of kelvins. Now let me pause here. In astronomy, we use a different temperature scale. You're familiar with the Fahrenheit scale, you're probably familiar with the Celsius scale. The Kelvin scale is the one that we use in astronomy. In one sense, it's the same as the Celsius scale, except that in the Kelvin scale, it begins at absolute zero. So, whereas on the Celsius scale, it's 200 some odd degrees below 0 Celsius. Okay, the Kelvin scale begins at absolute zero. And when we talk about the Kelvin scale, we use the language is a little bit different. So instead of saying 10 million degrees Kelvin, we'll just say 10 million kelvins. That's what we're talking about. So that's the temperature scale we'll be using in this course. So they measure these temperatures in the ranges of tens of millions of kelvins, and we determine this by X-ray analysis. And this was discovered in the 60s. Well, how does that work? Well, again, it has to do with understanding how waves work. One of the basic formulas for waves works this way. First of all, velocity of a wave the velocity of a wave is equal to its wavelength times its frequency or another way of putting it, in astronomy terms, since we're going to be looking at, spending most of our time looking at light, we're going to say c, that's the speed of light, equals wavelength, Greek letter lambda, times f. All right. Now, how is that relevant? We'll get there. Temperature, we need to be clear on what we mean by temperature. Temperature is a measure of the kinetic energy of atoms Let's try it this way. The average kinetic energy of atoms and molecules in a given sample. Okay, so kinetic energy, what do we mean by that? Well, it's the energy of a moving object. So if I had a 2-pound rock, roughly 1 kilogram, if I had a 1 kilogram rock, roughly 2 pounds, and I dropped it from a height of say 4 feet and it hit the floor at that velocity, it would deliver roughly 10 joules of energy. All right, so that's one way of looking at kinetic energy. Kinetic energy is it's the energy of a moving object. So temperature is the average kinetic energy of a given sample of atoms and molecules. Okay. Wavelength, frequency are related to the energy levels of the electrons. And in a nutshell, the higher the frequency, the higher the energy. This is how atoms work. All right. So again, there's more stuff that we're going to have to get into. I don't want you to feel discouraged or overwhelmed. Remember, we are at the finish line of this course, not the beginning of the course. This is stuff that is going to pertain to the finish line of this course. So energy level of electrons. Well, that means that we're going to have to understand what electrons are, how they work, and I can give you a quick idea. Okay, so here's my standard Zippo, and I've just flicked it on, and we see the flame. And we were taught in school that the reason that we see that flame is because the air is being heated up. Well, that's only partially true. It's actually a cooling off process that allows that light to be emitted. Let me just show you this. This is just going to be the quick and dirty. Okay. We'll start with a very simple atom, the simplest of all atoms, a hydrogen atom. So, a hydrogen atom has a single proton in the center and an electron orbiting around it. Now, let me zero that in a little bit better. Okay, so there's my proton. Here's my electron. All right. Now, if I apply heat to that, that atom, what's going to happen is that electron is going to jump out into the high-speed lane. This is a street fighting version of that. Okay, he's going to jump out into the high-speed lane. He's got more energy, so he's going to be zipping around quite a bit faster. But eventually, he's going to drop back down into the slow-speed lane. And in order to do that, he's going to dump some energy. How does he do that? Well, he emits a photon. A photon is a particle of light. All right. So what are photons? Well, in a nutshell, photons are electron poop. That's what they are. Okay? But it's a photon, and so yeah, it's a particle, but it also has a wave type characteristic to it, because we're talking about light. So that means it's going to have frequency, velocity, and wavelength. And the more energy, the more kinetic energy that photon's got going, is when it dumps that energy, it's going to emit the photon at a higher frequency. And we'll get into this in greater depth, but just understand this for the time being. If you look at a spectrum of visible light, where you've got red at one end, blue at the other end, and in between, you got orange, yellow, green, and so forth, and then you get violet to the very end. All right. At this end, it's low frequency and long wavelength. At this end, it's high frequency and short wavelength. Okay, this is visible light. Now, beyond visible light, we get into infrared, okay, and then we get into radio waves. But they're all photons, believe it or not. Radio waves, infrared, it's all photons. Photons is photons. At the other extreme, we get into ultraviolet, and then X-rays, and then gamma rays. All right. So, when that electron is in what we call an excited state, the faster it's going to move, the higher the frequency. So that's why we can say higher the frequency, higher the energy. So this is why we say we get into X-rays and gamma rays. That's extremely high frequency. That's got a lot of energy to it, and that's why X-rays and gamma rays ain't good for you. All right, because they have a tremendous amount of energy. That's why radio waves don't hurt you so much, because they're very low energy. They're going right through you right now as we speak. Okay, but that's the basic idea. All right. Now, because we can measure the wavelengths of light from these distant objects, and again, just to emphasize this, whether it's radio waves, visible light, X-rays, gamma rays, it's all light, because photons is photons, all right? They're all photons. And the only difference between them is what the frequencies and wavelengths are. That's it. In a sense, our eyeballs are like radio receivers. They receive only a certain range of wavelengths. And that's why your cell phone, which runs on radio, doesn't pick up FM radio as such, because the FM radio is at a different frequency or wavelength. Okay, it's the same sort of deal. But we have instrumentation whereby we can measure the frequencies. If we can measure the frequency, we can measure the energy. Okay, that's it. So now we know what the temperatures are by measuring the frequencies of the light being emitted by these areas. And here's what it tells us. We know that these gases are in gravitational equilibrium. The higher gas temps produce greater outward pressure. That would make sense. Okay, yeah, higher gas temps produce greater outward pressure. Well, yeah, we know that. That's why we don't throw aerosol cans or Bic lighters into the fireplace. All right. 2, gravity produces inward pressure. Well, yeah, that makes sense. And number 3. Inward pressure produces and maintains temp. Finally, mass calculations from these observations concur they concur with the mass calculations of Zwicky and Rubin. Now, let's get back to this idea of inward pressure producing and maintaining temperature. If you've ever used a bicycle pump, you know, especially the one that's a big long column with a handle on top, and you do one of these jobbies with it, you may have noticed that the barrel of that pump gets really hot. And you may have assumed that that's because of the friction of the plunger down inside that tube. And to be sure, that would generate some of that heat. But what's really making that bicycle pump tube so hot is the pressure you're putting on that air. That's what causes the heat. These atoms are moving around at a certain speed, like bees in a jar. And when you push them together, they're going to move faster. A way to think about it is this. If you remember your high school chemistry or your high school physical science, electrons have a negative charge, protons have a positive charge, and if you push two negatively charged objects together, they're going to repel. Just like if you had a pair of magnets and you pushed the north poles toward one another, the closer you get them, the more they're going to repel. And if you let them go, they're going to move away even faster. Okay, so the same sort of thing is happening here. Those atoms want to push apart from one another, but you're forcing them together. And as a consequence, they move faster. And if they move faster, then they got more kinetic energy. It goes back to our definition of what temperature is, the average kinetic energy. All right? So this is what's going on here. We have a certain amount of mass that's causing a certain amount of gravity pulling stuff in. And if you've got gases that are being pulled in and compressed, they're going to heat up. And if they're going to heat up, they're going to try to push apart. But if there's enough mass there and there's therefore enough gravity there to keep them pushed together and maintain that temperature. This is an important concept. This is going to also read into how stars form. We'll see that one down the road. The other way to think about it is this. I'll bring up this topic again, but at a later time, but we'll touch on it now. It's important to, a way to understand that is to understand the difference between a gasoline engine, a gasoline internal combustion engine, and a diesel internal combustion engine. The big difference between the two engines is that a gasoline engine has spark plugs that generate a spark every time that cylinder comes around. A diesel engine has a glow plug that is used only to start the engine, and once the engine is started, the glow plug shuts off. Well, we know how the gas is ignited in a gasoline engine. Every time that cylinder comes around, there's a spark, touches off the gas, and boom, you've got compression. In a diesel engine, it works differently. Once that diesel engine is started, it doesn't need a spark plug to ignite the fuel. What happens is the diesel fuel is injected into the cylinder comes up and compresses that diesel gas in an aerosol form, and by virtue of the pressure alone, it causes it to heat up until it reaches ignition point. It's the pressure itself that ignites the diesel fuel. Same sort of thing is happening here. All right, so we have this tremendous gravitational pressure pulling this gas in between galaxies. Okay, that's causing that gas to heat up. The heat would make that gas want to expand out, but there's too much gravity, too much mass for that to happen, and so it keeps it in place. And by measuring that amount of temperature and measuring the area that this gas is taking up, they can deduce how much mass is in play here. And what they have found is that there's more mass than what they can readily observe. And again, it is consistent with what Zwicky had to say concerning the orbital velocities of galaxies, what Rubin had to say concerning the rotational velocity of individual galaxies. And it's also consistent with the measurements that we've been able to make with gravitational lensing. We know how much mass there is required to make how much curvature in space-time. And so here's the big takeaway up to this point. 3 separate independent lines of evidence to support the existence of dark matter. The first line of evidence, rotational velocities of galaxies and orbital velocities of galaxy clusters. That's one. The second line of evidence is gravitational lensing as predicted by Einstein. Verified, done, measured. And the third line of evidence is the temperatures of the gases in the intracluster medium. 3 separate independent lines of evidence that nevertheless render the same results mathematically. Okay, so we have, and that's important because we have 3 separate and independent lines of evidence that still come up with the same conclusions, still come up with the same numbers. That's pretty compelling. All right, so we're going to stop here and go on to the next topic here in the next video.